We are from the team 1097. We give you the solution for the problem C, people doing everything. Our team have Damon Spencer, Morgan Kortlander, and me, Natalie Pham. We are from University of Houston. About the problem statement, we learned that the introductions of humans into a predator-prey system can reduce the anti-predator response of the prey. So we want to develop a mathematical model of prey and predator populations over time before, during, and after human occupation. We did make some assumptions. First, we observed that when the prey population increased, the predator population also increased, and when the predation going on, the food source going to starve, and the prey population decreased, so on the predator population also decreased. Secondly, the human occupation results in muting of prey anti-predator behavior, and the human presence also reduce the activity range and area of predators, and so on. The predator population will reduce over time. As per the problem stipulation, human presence has both rapid onset and egress. So anti-predator response of the prey population, they need energies, and if anti-predator response increase, the prey will less likely to find food, mating, and also reproductions. However, the survival probability will increase. Next is about the environment. We assume that the environment has limited resources or a carrying capacity, so the population cannot tend towards infinity. The anti-predator response takes time to change. And lastly, the predator population needs 5 times as many prey to support it on average. Next, we will give you some insight about our inspiration for our equations. So our model will be a combination between two models. Firstly, is a Lotka-Volterra equations. So Lotka-Volterra equation will model the rate of change of the prey population and predator populations as the functions of prey population and the multiplications between prey and predator population. As you can see in the screen, the two equations, 1 and 2. The next one is the logistic population model, as the rate of change of a population over time is equal to the growth rate times the population times 1 minus the fraction between the population and carrying capacity. As the third equation you see on the screen. So next slide will be Damon talk about differential equation development and defining.
Hello, my name is Damon Spencer. I'll talk about the development of the model. We express the function modeling the decrease in the anti-predator response with the introduction of humans as A of t. A of t increases as the humans enter and decreases as the humans exit. Hn and h out of t are functions representing the change in humans. Hn and h out of t are Heaviside step functions. They are both defined as time-shifted Heaviside step functions, and the humans enter at tau 1, exit at tau 2. Next slide. We considered using compressed time-shifted sigmoid functions as the switch for human presence in order to preserve function smoothness, but we decided on using the Heaviside step function to minimize model complexity. Since MATLAB both natively includes the Heaviside step function and evaluates ODEs using numerical methods, discontinuities in A of t do not present an issue. Our time unit t is in weeks, and we express the rate of change in prey population as dr over dt equals alpha r minus beta pr times r 1 minus r over the carrying capacity of prey. Alpha increases as A of t increases, and beta decreases as h of n increases, and increases as h of out increases. The carrying capacity of prey is the maximum carrying capacity minus 5 times the predator population. Next slide. The rate of change of the predator population can be modeled by dp over dt equals delta pr minus gamma p times p 1 minus p over the carrying capacity of predators. Delta delta has a base rate and it decreases as h of n increases and increases as h of l increases. H of n and h of l essentially cancel each other out. So delta decreases temporarily whenever humans come in and increases whenever humans come out. Gamma is constant and it's multiplied by K9. The carrying capacity of predators is 0.2 times the prey population. Next slide. There's a table of parameters. These are the values for all of our parameters in our ODs. R0 is the initial prey population at 5,000. P0 is the initial predator population, 2,000. The maximum carrying capacity of prey is 20,000. The human entry time is 300 weeks, and the human exit time is 700 weeks. The rest of the parameters are defined in the table. Here's a visualization of our simulation. The prey population increases rapidly initially and overshoots past 10,000 prey. The predator population increases to about 2,000 predators. Then, whenever humans enter, the predator population almost dies off and the prey population almost shoots to the maximum carrying capacity. So humans really do ruin everything. Then, whenever humans exit, the prey population returns to normal and the predator population overshoots a little bit, but it ends up returning to normal too. So things get restored. Next slide.
Hi, I'm Morgan Kortlander. I'll be doing the discussion here. So the predator-prey system did have a distinct change under the influence of humans, as we saw in the previous slide. And we observed some limitations in the model. First, the anti-predator response is considered a baseline effect that is removed by human presence. So a potential solution for this is writing the anti-predator response as a function based on both the predator population and the previous duration of predator presence to better simulate the prey learning. And another model limitation was that we did not show the strong oscillatory nature of pred-prey interaction in here. And we figured that we could more closely mimic the Lotka-Volterra model to start and incorporate the anti-predator response first. So we could get a model more similar to the expected Lotka-Volterra oscillations and then add in a human effect. So we could get something more along the lines of what we expected. And after that, we'd also observed that potential resource exhaustion was not accounted for with the rapid increase in prey population. So we were thinking that we could add in resource exhaustion effects by adding a decay term to the prey carrying capacity that increases the longer the prey population stays close to the ceiling. And since the stipulation, as mentioned before, was that introduction of humans to the environment was rapid as well as their evacuation, we simply used a step function with the Heaviside function. In a more complex model, we could consider using a sigmoid function, as mentioned before, to represent a more gradual onset removal of human effects, having a smoother function. And finally, for limitations, we noticed that the populations were asymptotic at extreme values, so extinctions are not really simulated here. And a potential solution for that is penalizing the birth rate nonlinearly at low populations to get a tipping point that a population may not be able to recover from. Thus, we'd be able to better simulate an extinction effect. And moving on to our conclusions. Our model did show a pred-prey environment that reached an equilibrium before introduction of humans, an equilibrium with human presence, and a return to equilibrium after human presence. So we were able to simulate an ecosystem that recovered after anthropogenic change. The pre-human equilibrium didn't have as much oscillatory behavior as we initially expected, but it did simplify the model in terms of human effects, since after 250 weeks, we no longer had to worry about what point in the pred-prey oscillation cycle that humans were introduced. For instance, it could have had a different effect depending on if humans had been introduced at a peak of prey population as opposed to when it bottoms out. And we chose simplified function speller model, but we think there's a lot of potential for predictive capability if we incrementally incorporate more complexity, although there will be a trade-off in the ability to interpret the model. And on the next slide, you can see our references that we used for this. And finally, we'd like to thank you for this opportunity for Explore modeling. and for your time and consideration in evaluating our presentation. So we had a lot of fun, and we hope to do it again.